All right, hey everyone. So this is the lecture for Chapter 3, Ions and Ionic Compounds. So it's a lot of practice involved in this one, like naming compounds and stuff. You'll learn the rules, and then you'll go through and just do some practices. So I want to address a couple things in Alex before we get on to the lecture. I've put up some material in Chapter 3 on your Cougar View. So these are once again supplemental videos. If you get hung up on any individual topic that is in this chapter, you can come to one of these videos and look for a different explanation. I have some students that say they just do this and it works fine. And then I have others that don't use these at all. So it's completely up to you how you want to use these. I like to provide it just so that you have multiple options, right? We have the text, you have these lecture videos, you have the YouTube videos, and I've also provided PowerPoints for this chapter. So you can go through there and use those as well. I'll kind of pull from all different kind of things and do my own drawings and stuff for this lecture, uh, as I always do. I just all over the place for the most part. So I do want to talk about Alex and make sure that everybody is staying up to date with your assignments. Okay, go in. I think you got one due this Wednesday, one due this Sunday. Talking about my fall 21 course. So get in there and work as much as you can. So let me just kind of show you quickly. If you once you get into a problem, so this is something older that you should have already done. But once you come into this problem, you have your text on the left. You can open that up and go to the section that it's discussing and look there. But my favorite thing to do when dealing with these, if I'm confused at all, is go into the explanation at the bottom left. Okay, once you click on that, it'll show you a problem very similar to what you're going to work, and it'll go through, show you how to work it, and give you a practice problem with the answers at the bottom. So you can go through, test yourself, make sure you're doing it correctly, then click on more practice, and when it takes you in, you're back working on Alex. So give it your best shot here, because if you miss these, obviously you know how it works. You get set back. If you get it right, you go forward. But these all contribute toward your grade. So if your grade is not 100%, you can go in here, work this some more, and continually increase your grade. Okay, so for those of you that have already completed it, I think it's in the review section you can click on, and then click, it'll bring up stuff that you've done in the past, and you can continue to work on that. And if you don't already have 100 on it, it will add it towards your grade. All right. So that's it for Alex. We'll come back and do probably a couple problems from this section once I get toward the end of the lecture. But I wanted to show you all that. Make sure you're staying up to date. It's kind of hard for me to put extensions on the assignments. And secondly, you lose credit. You lose um, the possible amount of points you could get is reduced, right? Like if you have to get an extension and turn in late, it might only be 90% as opposed to 100%. Okay, so just forewarning there. And let's get into chapter 3. All right, so a lot of the things that we learned in chapter 2, like electron configuration, valence electrons, and Lewis dot structure, we're going to kind of use here to introduce bonding. So it's important that you already have that kind of base knowledge in place before you get here. All right, so I'm going to go to the text. I like the text a little bit better for this section. So it's chapter 3, section 3.1. You can pull up the table of contents here on the left. This is the ebook that you should get with your Alex program, and all the different sections that we're going to be discussing. So I'm going to move kind of quickly through all of this because most of it is like naming compounds, which are essentially just a set of rules. You follow the rules, and that's then you just get the practice in. Okay, just keep practicing. You'll get better and better at naming it. Have a periodic table available so you can go quickly back and forth reading symbols and getting the names or whatever. All right, and then also to be able to keep up with valence electrons, because part of this is knowing how many valence electrons they'll pair up with others that have a certain number of valence electrons, and it kind of fits together like puzzle pieces essentially, but very easily identifiable puzzle pieces. Okay, so talking about binding. So binding or a bond is just a term that we use to describe how two atoms are connected, right? I have my little molecule here, and this little connection between the white and the black here is my bond, okay? And we use different terms to kind of describe these bonds, what holds the atoms together. There are ionic bonds and covalent bonds. And the difference is in the way that they share electrons. So just pull up my paint program real quick. Um, so remember when we did valence electrons, first let me go to the internet. We said that the valence electrons are pretty much directly from the periodic table, right? Y'all looking at, okay, yeah, the periodic table. So everything on this far right side is what we call a noble gas. Noble gases don't really form bonds because they have their 8 valence electrons, right? I've drawn argon here as a Lewis dot structure with the 8 valence electrons around the outside, and you'll see that argon is indeed in group 8 on this far right side. So all of these will have the full octet. They will have the 8 valence electrons that it likes to have, therefore will not bond. Okay, so others will share electrons. For example, let me clear this out. Let's do carbon and hydrogen. Okay, carbon. Actually, I'm going to start by putting the valence electrons. So carbon is in group 4 and has 4 valence electrons. Okay? Now, when it combines with something, because it would take a lot of energy for carbon to hold 4 electrons from space, what ends up happening is it will share electrons with another atom in the general vicinity. Okay, so for example, a hydrogen. So if I have 4 hydrogens just sitting around, I could share those electrons from the hydrogen with this carbon here. Okay, these are called covalent bonds. They're covalent because the electrons are shared between the two. Each one of these bonds is actually a representation of 2 electrons. Okay, and those electrons can be found anywhere in this bond. If I pull out right here, I can get an electron. If I pull out right here, I can get an electron. If I pull out right here, it's essentially they're just moving back and forth from one atom to another. So you can always find an electron in the bond. Now the difference between that and the ionic bond is that in an ionic bond the electrons are given away. All right, the atoms are still held closely together, but they're not sharing the electrons. And I'll explain why in just a second. Let's do table salt. Okay, so I'm going to write sodium, the chemical symbols for sodium and chloride here. I'm going to fill out my valence electrons just like I did with argon and with carbon and all those. Let me go back here. Alright, so 1 valence electron for sodium because it's in group 1. Come back here and show you all that. Right, sodium on this left side. I can't click on it. Sodium right here on this left side. Alright, so that's group 1, 1 valence electron. Chlorine is over here on the far right and has 7 valence electrons. So let me put those 7 right here. 1, 2, 3, 4, 5, 6, 7. Okay? So now, general rule of thumb, the octet rule, we like to have 8 valence electrons around our atom, either 8 or 0. Those are the two most stable configurations, is what we call them. So I have a sodium here with 1 valence electron. It would really like to get to 0. I have a chlorine here with a 7, and it would really like to get to 8 valence electrons. So what ends up happening is the sodium will actually give the chlorine this electron. They'll hold very tightly together, but they do not share the electrons. Okay? The chlorine holds all of the electrons over here with it, and the chlorine holds none of them. So this is how table salt is held together, just with these electron bonds called ionic bonds. All right, and the reason that they stick together so well is not because the sodium just gave up the electron, it's because when it did, the sodium became positively charged and the chlorine became negatively charged. Remember, we said electron carries a negative charge. So if the sodium has one less electron, it becomes +1, a cation. And the chlorine, gaining one more electron than it should have, becomes -1. This difference in charge, right, electrostatic forces, is what creates the pull. Remember, opposites attract. So the sodium and the chloride kind of pull in very tightly together, and thus we have a bond, but the electrons are not shared. They're given away to the other one. Okay? So that those are ionic and covalent bonds, and just kind of a brief explanation of what's going on here when it talks about the transfer of an electron versus the sharing of an electron. Okay, and you'll notice the pattern here, right? The sodium tends to bind with the chloride because it's a 1 plus a 7 equals 8, right? So similarly, let me go back to the periodic table. Magnesium, which is in 2 plus, right, might tend to bind with oxygen because it's a 2 minus, right? This has 2 valence electrons. This has 6. So 2 plus 6 equals 8. That fills that octet, and they can kind of form this ionic bond. So you will always see ionic bonds form between elements on the far left side of the periodic table with elements on the far right side of the periodic table. Okay, if it's a transition metal, more than likely it's a covalent bond where electrons are being shared. All right, but not always. So just keep that in mind. Typically, ionic bonds are formed between those on the left side of the periodic table and those on the right side of the periodic table. All right, let me go back to, let me kind of keep up with the PowerPoint and the text so I can kind of roll through. Yeah, so any metal and non-metal, that's how they kind of refer it. Remember, metals are all the things on the left side of the periodic table, including transition metals. So they do include transition metals. And then every non-metal is everything on that P block on the right side of the periodic table. So we talked about that. Okay, ions, when we talk about ions, ions just mean that they're charged, okay? Anything that has given up or accepted an extra electron has become an ion. So back to my little paint program here. We said Mg earlier. We'll undo that, cut that. Mg has 2 valence electrons typically. It will pretty much always lose those 2 when it becomes an ion, okay, because it likes to get to 0. So Mg becomes Mg2 plus. Everything that loses electrons or everything that's positive is called a cation, okay? And then everything that gains electrons, like the chloride that we were looking at earlier with 7, right, becomes an anion. Anions are negatively charged ions. Ions in general are just something that has gained or given up an electron, okay, and has become charged as a result of that. So just remember, if you see a charge, you can think of, well, that's an ion. All right, so this will be -1. I'll put 1 minus, but usually we don't put the 1 there because we just throw the minus charge up at the top. Typically what you'll either see is the minus like that. Sometimes you'll see it circled. Sometimes they'll do 1 minus. Okay, so you can see it all different kind of ways, but either way we're just telling you that this is charged. This thing has 1 extra electron than it should, right? Because it's on row 7 of the periodic table, group 7 of the periodic table. All right, where was I? So cations, anions, what are ions? Shouldn't have any problem with that. It is important that you notice that you keep up with the valence electrons, right? So what group it's in, how many around that outermost shell, essentially. And we talked about the octet rule. That just means you have 8 valence electrons. You would like to have 0 or 8. All right, and so most all of reactions or chemical compounds are seeking to accomplish that. All right, they're seeking to get 8 electrons around an atom, 2 around a hydrogen and a helium. Remember that hydrogen and helium can only have 2 because they only have 1 orbital. And I mean, we've kind of discussed that. That's just saying that your group number is a good indication of what charge you're going to have, right? So going back to the periodic table, if I'm over here on this left side, beryllium, for example, I want to get to, I used to call them end zones. The end zones is 0 valence electrons on this side and 8 on this side. So in order for beryllium to get to the end zone, it needs to give up 2 electrons. It's got 2 more than it needs. So if I give up 2, I become positively 2 charged, right? And I can get to the end zone. On the other side, fluorine, chlorine, bromine all like to add 1 electron to get over here to this end zone. Oxygen will like to add 2 to get over here. Nitrogen and phosphorus will like to add 3 to get over here. Okay, and so it's just a continuing pattern that you'll see when it comes to ion and ion pairs and even bonding in general. Okay, when you get to more covalent bonding, you'll see that even those covalent bonds are sharing electrons in an attempt to get the octet full. All right. And some of those videos that I put on from YouTube are really good. They kind of walk through the pairing, the different kind of pairings that you'll see. But as a general rule of thumb, you can pair any 2 together as long as you balance the charges. Let me go back to the text. I like it better than the PowerPoints. But it all follows the same kind of pattern. Don't forget about these little practice problems, so just kind of test yourself. Um, Predict whether the bonds in the following species are ionic or covalent. C and O. So just quickly, I can go to my periodic table. Make sure y'all can see that. Yep, C is on the same side as O. They're both nonmetals. So I'd say that's not an ionic bond. Remember, ionic bonds have to be on one side and the other. It has to be a metal and a non-metal in order for it to be an ionic bond. So that is definitely a covalent bond. B, calcium fluoride. Go back here, show you where fluoride is on the far right. Calcium is on the far left. Calcium right here. So that will be an ionic bond. Since they're on opposite sides, I can assume that one is giving away electrons to the other. Magnesium oxide. So oxygen over here, magnesium over here. That's going to be ionic, opposite sides. Cl2, okay? Both of the Cl's are on the right side of the periodic table, so that's got to be a shared electron, okay? It cannot be an ionic bond because they're too close together on the periodic table. It wouldn't make sense for one to give the other electron away. They'd have to share it for it to make sense. And you'll see more of that when we get into covalent bonding. Hydrogen fluoride, so fluoride's on the far right, hydrogen's on the far left. But you have to be this. I would not call an ionic bond. Well, yes, I would. This is an ionic bond. The hydrogen will give the electron to the fluoride and get to a zero, but I guess they could just as easily as share it and get to that stable conformation as well. But we know that the hydrogen likes to. That's a little bit tougher one. I would call that ionic. All right, and then C2H6. So that's definitely covalent, just because the carbon and the hydrogen are very close in electronegativity, which is how much they want electrons. Both of them really like electrons, so they're not going to give it up as easily. It can so with the fluoride because the fluoride's so much stronger in electronegativity than the hydrogen, but not in the carbon. So this is a covalent bond, and you should just remember that anytime you see a carbon bound with a hydrogen, it's going to be a covalent bond. Okay, uh, that's just kind of how organic chemistry works. They share those electrons; they don't give them away. All right, so that's enough review for that. Let's go to the next section. Um, Ionic compounds. So we just kind of did this a minute ago where we showed you that one will give away an electron, creating a charge on both atoms. And then those atoms with the oppositely charged ends can kind of stick together just based on electrostatic energy, kind of magnetic, if you will. They kind of stick together. But an important thing to remember when it comes to this is I can share between multiple atoms. So you'll see a lot of times um, two lithiums will donate both of their electrons. Each lithium offers an electron, so it takes two to balance out an oxygen, right, which has a charge of 2 minus. And all this is coming straight from the periodic table. Okay, I don't want y'all to get lost on that. The 2 minus is because oxygen's in group 6 and it requires 2 more electrons to get over here to 8. And then the lithium is on the far left. I have to bring this down, and it can give up 1 electron before it gets to 0 valence electrons. So that's how come lithium's always at a +1 charge and oxygen's always at a 2 minus charge. Okay, until for ionic compounds. So the most important thing here that you should take away from this is that the charge is always balanced. It doesn't matter if I have 3 of one molecule, 2 of another. Um, we can continue to add in atoms until we balance those charges. So when you go to work on Alex, this is what it's going to kind of test you on. It'll give you this big complex ion, and it'll say it has a minus charge. And you need to pair it with, say, a lead, Pb 4 plus. Okay, where's lead at? Down here. Pb 4 plus. So you'll have to mix 4 of those chlorides or whatever had the -1 charge with this 1 Pb to make the charges balance. All right, and so I'll get into that a little bit more here in a minute when we start writing out compounds and formulas for those compounds. Okay, so the kind of general rule of thumb, I'm looking at these steps that it's telling you on how to write formula of a compound. I'm not going to go through every step because Each one kind of does it differently. I've just kind of absorbed it by now, and I don't want to confuse you. So I'll let you go through these steps and kind of figure out how to write the formulas. But a general rule of thumb is look for the non-metal on the right. Okay, and the reason that is almost always fluoride, chloride, bromine, iodine are going to have a 1 minus charge. Okay? When it comes to ionic compounds, for sure, they're always going to have a 1 minus charge. Oxygen, sulfur, selenium are always going to have a 2 minus charge. Nitrogen, phosphorus, arsenic will always have a 3 minus charge. So, what does that mean? That means if I see any metal paired with one of these that I know for a fact, then I can calculate the charge of that metal. And you'll see different metals. Sometimes they'll come at you with a copper, which can be 2 plus copper, or it could be 3 plus copper. You don't know. You have to figure out based on what it's paired to. If copper was paired to, say, 2 chlorides, I would say it's Mg is copper 2 plus. If it's paired with 3 chlorides, then I know it's copper 3 plus. You see what I mean? I'll do some more examples when we go do our Alex here in a minute. But that's just kind of a general rule of thumb I like to use. I pick something that I know what the charge is, and then I figure out what the other one that it's connected to is. Okay? Sometimes it'll tell you, other times it won't be that easy. But if you kind of keep that in mind, that all of these have very predictable uh, ion formations, then you can backtrack and kind of back calculate which one it is. Similarly, on the far left, okay, just for these first two groups, the sodium, hold on, let me minimize this. Lithium, sodium, potassium, rubidium always have a plus 1 charge. Beryllium, magnesium, calcium, strontium always have a plus 2. Okay, so you can also use those and go the other way. If you know that I have a beryllium 2 plus and it's bound to 2 chlorides, I can figure out that each chloride is 1 minus. Okay, so that's how you kind of pair the ions together. Now let's go back to writing the formula. They're just basically the gist of the rules is balance the charges based on the valence electrons. So exactly what we've been doing. Once you balance them, you can figure out how many of each you have, and then you just name them cation first. Okay, so always the metal first. Potassium chloride. You drop the ending on the non-metal and then add IDE. So calcium fluoride, magnesium oxide, uh, I don't know, francium sulfide. Okay, so it's not actually that difficult. You get a couple times through, and you'll kind of figure it out. The tougher part is going to be identifying polyatomic ions, which is at the end of this chapter. And it has some different little rules for like being able to differentiate or tell the difference between uh, chromiums of different charges, irons of different charges. So you see you have ferrous and ferric. So OUS for the one that's lower in charge, uh, RIC for the one that's higher in charge. That's just kind of little tidbits. This is where you drop the ending and add IDE. Always write the cation first. So I'm not going to go through and do a bunch of these because, like I said, it's just practice. You'll get it. Name each compound: sodium fluoride, magnesium oxide, strontium bromide, lithium oxide, titanium oxide, aluminum chloride. You get the gist. It's the same drill over and over and over. Every now and then you'll get something weird like with the ferrous or ferric oxide, whatever. Um, I honestly just say iron oxide, and then I put my Roman numeral in there. So depending on what Alex asks you, you might need to be familiar with the other way. All right, so that's pretty much self-explanatory. Let me go. I think we need to do polyatomic ions. Real quickly, I'll cover some of the properties. So, ionic compounds like salts, I tend to think of ionic compounds as being salt, which essentially they are. Sodium chloride is one of the most common ionic compounds you'll run across on a day-to-day basis. All right, sodium chloride has a very high melting point. Okay, so all salts kind of follow have those these same properties. Okay, salt has a very high melting point, and in most cases you're just not going to melt many salts, and that's because of the way that they're bonded is different than the way that a covalent bond works. If I start talking about covalent bonds, we're talking about gases and well, yeah, gases and even oils, gasolines, okay, things that have a lot of energy and are very combustible, perhaps at a very low temperature even. So very different between the bonding of ions and then covalent bonding where electrons are shared. Okay, ionic compounds are they're hard to melt, they're hard to boil, they're soluble in water because of the charges. So it's interesting. I can't melt it and I can't boil it off into a gas, but if I put it in water, they'll break up as easy as anything. You know, they'll just break up automatic. So salts are very interesting in that, and that has to do with those charges, right? If I have a negative on one end, a positive on the other end, of water, which also has positive and negatives in it, can kind of just cut through it, no problem, right? But if I heat it up, it essentially makes those bonds stronger for the salt. So that's interesting. Not too much to know there. Perhaps you might get something like that on the midterm exam where I'll say, "Hey, I have a substance here. It boiled at 100 degrees Fahrenheit and there was no residue left behind. Was there any ionic compound in my solution?" And you'd say no, because the salt wouldn't have boiled away at 100 degrees. The water would have, but the salt would have still been there. Okay, so now the polyatomic ions. My best advice for polyatomic ions are just to keep a list of these handy until you get familiar with them and you can recognize them easily because you will see these uh, in your Alex assignments for one, but also in a lot of stuff going forward. So I would just kind of clip a little list. There might be one in the PowerPoint as well uh, that has all of the charges and the names of all these different polyatomic ions. So let me just look over these and see if this is most of the ones you'll see. I would imagine you'd see a few more, but I'm not sure. So definitely phosphate, hydroxide is a very common one. Sulfate's a common one. Carbonate, acetate, are all very common ones. So nitrate is a common one. So look, all the darkened ones are probably the most common. You see how some of them have a darker shade than others? Those are probably the most likely for you to see. All right, so I would definitely keep a list and just kind of use those polyatomic ions whenever you get a chance, and they work the same way as any individual atom. So, like, let me look at my periodic table. Say chloride is 1 minus, right? And when I go to pair it with magnesium 2 plus, I know that I need 2 chlorides to bind with 1 magnesium 2 plus. So when you look at these polyatomic ions, each ion has a charge associated with it. So I don't count up the charges like I did earlier. Say, let's look at nitrate. Okay, so if I were doing it like I did earlier, I'd say each oxygen has a 2 minus charge, and then the nitrogen is right here, so it would have a 3 minus charge, and my total charge for NO3 would be what 9 minus. Okay, that doesn't make sense. These are actually covalent bonds, so the nitrogen and oxygens are sharing electrons, and they've created their own little molecule here, but the molecule has a -1 charge. So you have to treat it as if it was a chloride with a -1 charge. If I go to put this in a compound, let me pull up my paint program. If I go to put this in a compound, let me do phosphate. Cut. So phosphate is PO4 3 minus. Okay. Now let's say I want to put this in with magnesium that is 2 plus. Okay. So remember, this ionic bonds and ionic compounds are all about balancing charges. So it would take 3 of these and 2 of these. All right. Because 6 is the least common denominator between the two. All right. So I have to get 2 phosphates together with 3 magnesiums. Remember to write the cation first, so it would be Mg first, and then PO4. And if you want to show that I have multiple, you have to do it as a subscript. So there's 3 magnesiums, that comes in as a subscript here. For phosphate, I need to signal that I want 2 whole polyatomic ions, so I put it in parentheses and do that 2 there. Okay, so now if I go back and figure out the charges, it's 3 times 2 plus, that'd be 6 plus worth of charges there. 2 times 3 minus will be 6 minus worth of charges on the phosphate. Okay, so that's how you kind of do these polyatomic ions. You're still balancing them the same way as you would a magnesium in a chloride or a sodium in a chloride. You just have to make sure that you keep them in parentheses and that you're moving them whole as a whole, because they are one molecule that all together holds that charge. All right. So that was one of the more difficult ones you'll see. Most of the times it'll be one like metal and then one non-metal, and then you'll have to balance out for the formula. But these polyatomic ions, you will have some mastering chemistry on Alex dealing with these. So I wanted to show you, just make sure you're moving around as a whole, and that you multiply everything by putting it in those brackets. Those little parentheses tells me that I need 2 whole phosphates. If I put it right behind that 4, it looks like I need 8 oxygens. Okay. What else? And the text goes through and walks through step by step how to do all this. So I just kind of give you the shortened version, my little shortened version of how to do it. But if you run into any problems, you can obviously email me or go look on one of your videos. I can do another private session if you need to ask specific questions and kind of have me walk you through it. We can do those on the weekends usually. Just send me an email throughout the week and we'll set up an appointment. But I think that is it for today. Yeah. So I'll see y'all when I post the next lab and walkthrough video for lab later this week. Later, y'all.